This video is a walkthrough of the solution to the bicycle wheel problem that I posed to learn about moment of inertia and kinetic energy. So if you haven't looked at that problem, you ought to take a detailed look at it first and then try to watch this video to answer your questions. The essence of the question is this. I'm imagining a bicycle wheel that has an outer diameter equal to 27 inches. That's what most bike wheels are. That's for the outer diameter of the rim and the tire. And then the rim and the tire are kind of thin, so only 0.875 inches thick. And the mass of the rim and the tire together is 1.25 kilograms. And then the wheel is connected to the axle at the hub by 36 spokes. And each spoke is 13.25 inches long and has a mass of about 18 grams. So these are pretty realistic numbers for a bicycle wheel. The first part of the question was to determine the moment of inertia of the entire bicycle wheel, including the tire, the rim, and the spokes. The reason why we want to know the moment of inertia is because the second part of the question asks about the kinetic energy of the bike wheel if it's moving and spinning at the same time. So in order to calculate the kinetic energy of rotation, we're going to need to know the moment of inertia of the wheel. So when you're working with kinetic energy of rotation, you're going to find that most of the time, finding the moment of inertia of the object that's spinning is the most problematic. Here's our plan of attack here. We're going to build up the moment of inertia of the wheel and the spokes using the formulas that appear in table 9.2 in your textbook. So that has various formulas for the moments of inertia of various shapes. The ones we're interested in here is the one for the hollow cylinders, one which has a very narrow wall and the other one that has a slightly slicker wall. And then we're going to have to come up with a formula that would calculate the moment of inertia of the 36 spokes. And then the total moment of inertia of the wheel is going to be what we can calculate for the tire and the rim and what we can calculate for the spokes added together. So moments of inertia just add in the usual way. So I think you'll find if you look in table 9.2 that there's two shapes that are approximately correct for our wheel, at least the rim and the tire part of it. One is a hollow cylinder that's not infinitely thin, and for that thing the moment of inertia is 1/2 times the mass times the sum of the two radiuses squared. So that's the inner radius and the outer radius squared and then added together. The other one is if the tire and rim are just infinitely thin, then we can just calculate the moment of inertia using mass times radius squared. So you're going to have to become quite familiar with the entries in table 9.2. You don't have to know why the formulas for moment of inertia are what they are. You just have to know how to use them. So in this particular case, we're going to calculate the moment of inertia both ways to see if it makes a difference. To see if we can just use the hollow one or maybe the thin one, the thin-walled cylinder one would be better. I think it's pretty sure that the next thing we're going to have to do is make sure all of the quantities that we need are in SI units. So while the mass of the wheel is given in kilograms, so the tire and the rim together are 1.25 kilograms, we have the radius in inches. So we're going to need to figure out the inner radius and the outer radius of the wheel, but not in inches. We would need it in meters. So you might want to pause the video and see if you can get answers to those things. And in the next moment here, I'll show you what I got. So the outer radius is the diameter of the wheel divided by 2. So the diameter of the wheel is 27 inches. Divide that by 2, you get 13.5 inches. And then you have to multiply it by 0.0254. There's 2.54 centimeters in an inch exactly. So I get the outer radius of the wheel to be 0.3429 meters. Now the inner radius is whatever the outer radius is minus the thickness of the wheel. Notice that in order to do this, you can't subtract the thickness of the wheel and the rim, the tire and the rim, from the diameter. You have to subtract it from the outer radius. So that's what I get for the inner and outer radii of the wheel. expressed in meters, and also to 4 sig figs. I'll drag along an extra significant figure because this is a 3 sig fig problem and I don't want to accumulate too much error. So now that we have the inner radius and the outer radius, you can plug those into the two formulae we had for the moments of inertia to see what you get. You might want to pause the video and do that, and then I'll show you what I get and you can check your work and see if you've made any mistakes. In any case, this is what I get. If you use the hollow cylinder, the one that's not infinitely thin, you get 0.1378 kilograms times meters squared. And if you just use the thin-walled cylinder and the outer radius, you get 0.1470 kilogram meter per square. They're not exactly the same. First of all, I want to talk to you about the units of moment of inertia. The units are kilograms times meters squared, mr squared. Moment of inertia is always going to have that units. The other thing I want to mention to you is which one of those should we use for the moment of inertia of our wheel, at least the tire and the rim part of it. Well, they're pretty similar, but they're not exactly the same. They're pretty much the same to 2 significant figures, but we have a 3 significant figure problem. So I think we're going to have to use the more accurate, the moment of inertia for the shape that's closer to the actual shape of our wheel, our rim and tire. So I'm going to use 0.1378 kilogram meter squared going forward. But one last comment. You could get a little closer using the thin-walled formula. Maybe if you used r not as the outer radius, but maybe use the inner radius. Or perhaps the best thing to do would be to use the average radius, some measure of where most of the mass of the wheel and rim are concentrated. In any case, moments of inertia are always approximate, and you have to pick the formula that comes closest to the shape that you're dealing with. So I'm going to move forward with the moment of inertia of the rim being 0.1378 kilogram meter squared. Now we have to figure out what's the moment of inertia of the spokes. So you can take a look in table 9.2 to see what you think is the best formula to use for a spoke. But I think it's pretty obvious that you need to use the one for a slender rod that's rotated about its end point. If you think about a spoke, one end is attached to the hub and the other end is attached to the wheel, and it's spinning around the hub. So the formula for the moment of inertia of a single slender rod is 1/3 ml squared, but we have 36 of them, so we can just add them all together. So to calculate the moment of inertia of all the spokes taken together, I have 1/3 ml squared from table 9.2, and I multiplied it by 36 because there's 36 spokes. Now you might want to double check whether or not you get the actual moment of inertia that I get. You have to be aware, again, that you don't want to make the rookie mistake of not putting the input quantities in SI units. So you would need the mass in kilograms even though the mass of each spoke is given in grams. And you would need its length in meters. In any case, we're pretty much done with this first part. We can calculate the total moment of inertia of the wheel by adding together the moment of inertia of the rim, which we had before, and the moment of inertia of the spokes. To end up with the total moment of inertia, that's like 1.2 times 10 to the minus 1 kilogram meter squared. One thing about the way I've written that, I put parentheses around the least significant digit, just to remember that this really is a 3 sig fig problem, so I'm sure about the 1.62, and I would use that to answer the question, but if I calculate something further with the moment of inertia, then I would use 1.621, because we don't want to accumulate too much round-off error. So again, reiterating the fact that when you're doing a calculation that has a number of parts, you need to carry one more significant figure than you're going to need at the end. All right, what about the second page? Well, here's a summary of the whole document, if you like. We started off by calculating the moment of inertia of the rim with the tire, and we calculated the moment of inertia of the spokes, and we added them together to get the total moment of inertia. All right, so the second part is to calculate the total kinetic energy of the wheel if it's rolling along at 15 miles per hour. Before, we didn't have to worry about the fact that there are actually two types of kinetic energy: translational kinetic energy, usual 1/2 mv squared, and rotational kinetic energy, which is 1/2 I omega squared. There's really only one type of kinetic energy, and that's the energy that masses have if they're moving. But we express it differently for objects that are spinning versus objects that are translating. And when a wheel rolls without slipping, it's doing both at the same time. So we have to account for all the kinetic energy of all the parts of the wheel. So we would need to calculate its translational kinetic energy using the usual 1/2 mv squared, and we'd have to calculate its rotational kinetic energy using 1/2 I omega squared. So we have a few things going for us for this calculation. The first thing is we already know the mass of the wheel. But I do want to remind you, you need the mass of the entire wheel. Not just the rim and the tire, but the rim and the tire and all the spokes. And we already know the moment of inertia of the entire wheel because we just calculated that in the previous part. So I think what needs to be done here is, first of all, calculate what is the total mass of the wheel so we know what that is. And also, since we have the velocity expressed in miles per hour, we're probably going to want to get that into SI units of meters per second. So why don't you calculate the total mass of the wheel and also calculate the speed that the wheel is moving, but in meters per second, and again to 4 sig figs. You can pause the video and calculate that, and then pick it up here again, and you'll see what I got for the answers. All right, so I figure the total mass of the wheel is 1.5 kilograms for the rim and the tire, plus 36 times the mass of a spoke, but I put the spokes in kilograms, not in grams, to get 1.898 kilograms. And I calculate the speed of 15 miles per hour to be 6.706 meters per second. We've made conversions like that many times, or you could just look it up if you wanted. So what remains for you to do now is to pause the video and see if you can't smash those numbers together to get a number for the kinetic energy of translation. That'll come out in joules, and the kinetic energy of rotation, which will also come out in joules. So if you want to pause the video and try to calculate those things, you can check my work in the next moment. One thing, however, you need to account for the fact that omega and v, while not the same thing, are related to one another. They're related by the formula v equals omega r. So when an object rolls without slipping, then the axis that it's rolling around, here the axle of the wheel, has some speed vc, velocity of the center. It has to be equal to omega times the radius of the wheel. So I calculated first the angular rotation rate of 19.56 radians per second. And I guess now you're ready to smash the numbers together to calculate the kinetic energies. Here's what I get. I find that the translational kinetic energy, if you smash the numbers together, is 42.68 joules. That's to 4 sig figs, although we really only want 3 in the end. And I find the rotational kinetic energy to be 1/2 I omega squared, and that's 31.01 joules. You should get something very close. And then if you want to find the total kinetic energy of the wheel, well, you have to add those things up. And then ultimately we want to answer the question in a sentence, and that is the total kinetic energy of the wheel is 73.7 joules. Here I express the answer to 3 sig figs. The last part is very simple. We just want to figure out what fraction of the total kinetic energy is in translational and what fraction is in rotational kinetic energy. So here you have to take each one of the kinetic energies and divide them by the total kinetic energy and maybe multiply by 100 to turn it into percent. So if you want to pause the video and see if you can figure out the percent of the total energy which is in translation and the percent which is in rotation, I'll show you what I get in an instant. All right, so I find that for this particular wheel, just about 58% of the energy is tied up in translational kinetic energy, and something a little over 42% is tied up in the rotation of the wheel. The reason why this might be interesting to somebody who is a cyclist, for example, is maybe you would like to have less energy tied up in the rotation of the wheel. I mean, the wheel has to rotate if you're going to go forward, but you have to provide energy to rotate the wheel, and that doesn't really help you go forward. So what would help make a wheel have a greater fraction of its kinetic energy tied up in translation and a lesser fraction tied up in rotation? So if you decrease the mass of the wheel, well, it would decrease both proportionally. What you really want to do is make the wheel have a lower moment of inertia. If you think back to the original equations, the kinetic energy of translation is 1/2 mv squared, and the kinetic energy of rotation is 1/2 I omega squared, and v and omega are related to one another. You can't change one without changing the other by the same fraction. So the only way you can make a wheel have lesser kinetic energy tied in rotation is to make the wheel have a lower moment of inertia. Well, I hope that helped you understand this solution.